There is an object out there about the size of Manhattan that contains more mass than our entire Sunday. If you took a single teaspoon of it, it would weigh roughly 900 times the mass of the Great Pyramid of Giza. And if you somehow fell toward it, you'd be moving at a quarter of the speed of light before you even got close. This is not a black hole. This is something weirder, something physicists are still trying to fully understand. This is a neutron star, and what is happening inside one might be the strangest thing in all of physics. Stick with me, because by the end of this video, you are going to understand why these things exist, what is happening inside them right now, and why without them, you literally wouldn't be here. To understand neutron stars, you first need to understand the thing that created them: stellar death. Stars are not permanent. They're a battle. On one side, you have gravity, relentless, patient, trying to crush everything inward. On the other side, you have nuclear fusion. Hydrogen atoms smashing together in the core, releasing unimaginable energy that pushes outward. For millions or even billions of years, those two forces are perfectly balanced. Your star shines. It is stable, it is beautiful, but fuel runs out. For a star like our Sunday, this ends quietly. It swells into a red giant, sheds its outer layers, and collapses into a dim cinder called a white dwarf. Sad but gentle for the big ones. Stars 8, 10, 20 or more times the mass of our Sunday. It ends very differently. When they exhaust their hydrogen, they don't stop. They accelerate, the core gets hotter, burns faster, and starts fusing heavier and heavier elements in a desperate attempt to maintain that pressure balance. Here is the timeline, and this part is genuinely insane. Carbon fuses to neon, takes a few centuries. Neon to oxygen, about 1 year. Oxygen to silicon, roughly a few months. Silicon to iron, less than a day. You heard that right. A process that took centuries is now happening in under 24 hours. The star is burning through fuel at a catastrophic rate, and then it hits iron. Iron is the dead end of fusion. It absorbs energy instead of releasing it. The second iron builds up in the core, fusion stops. The pressure vanishes. And what happens next happens in less than a quarter of a second. The entire core of the star, something roughly the size of Earth, collapses. Electrons and protons, which really don't want to be next to each other, are now forced together by gravity, so intense that they merge. Forming neutrons, the whole iron core is being crushed into pure nuclear matter. An Earth-sized ball of iron collapses to something roughly 15 to 20 kilometers across, about the size of a city in under a second. To put that into perspective, we just compressed the mass of our entire Sunday into an object smaller than the island of Manhattan. And it happened faster than you can blink. The outer layers of the star, which were also falling inward at about 25% the speed of light, slam into this suddenly rigid core and bounce. The shockwave blasts outward with the energy of roughly 10 billion trillion watts. For a few seconds, this explosion outshines entire galaxies. We call it a supernova. It is one of the most energetic events in the observable universe. And it leaves something behind, that leftover ball of neutrons. That little city-sized object of death. That is your neutron star. Okay, let's actually wrap our heads around how insane this object is, because I don't think numbers alone do it justice. Let's use comparisons. Density 1 cubic centimeter, the size of a sugar cube, contains roughly 1 billion tons of material. That is like packing every mountain on Earth into something you could hold between your fingers. Or think of it this way, Mount Everest fits in a coffee cup. Gravity, the surface gravity of a neutron star is approximately 200 billion times stronger than Earth's. If you were standing on it, you'd be instantly compressed into a layer of atoms thinner than a sheet of paper. Surface temperature newly formed neutron stars reach surface temperatures of around 1 million degrees Celsius. For context, the surface of the Sunday is about 6,000 degrees. That is not a typo. A neutron star's surface runs nearly 200 times hotter. Magnetic field. The most extreme neutron stars, called magnetars, have magnetic fields roughly a quadrillion times stronger than Earth's. If a magnetar were sitting halfway between Earth and the Moon, it would erase every credit card, rip the iron from your blood, and collapse the structures in your body before you even noticed. And if it gets any denser than this, it crosses a threshold and collapses into a black hole. A neutron star is, in a very real sense, the last possible stop before oblivion. Now here's where things get legitimately weird, because nobody fully understands what is happening in the core of a neutron star. And that drives physicists absolutely crazy. Let's go layer by layer. The crust, the outermost layer, is actually a crystalline solid. Iron atoms arranged in a perfect lattice, with a sea of electrons flowing through them. Despite being the surface, this material is already millions of times denser than anything on Earth. It is the hardest material in the known universe. Nuclear pasta, as you go deeper, nuclei get squeezed closer and closer together until something bizarre happens. They start to merge into exotic structures, long tubes, flat sheets, that physicists have nicknamed nuclear pasta. You've got spaghetti, lasagna, the full Italian cuisine of doom. Nuclear pasta is theorized to be the strongest material that can exist, potentially 100 trillion times stronger than steel. And yet, tiny imperfections in it can create mountains on the neutron star's surface. Mountains that are maybe a centimeter tall, but contain more mass than entire mountain ranges. The core, this is where we genuinely don't know what is happening. Some physicists think the pressure gets so extreme that protons and neutrons dissolve entirely into a soup of their constituent quarks, forming what is called a quark-gluon plasma. The same state of matter that existed microseconds after the Big Bang. Others think exotic particles called strange quarks dominate, creating a type of matter called strange matter, which, if it ever escaped a neutron star and touched normal matter, might theoretically convert everything it touches into more of itself. Or maybe the core is just densely packed neutrons, we don't know. We literally cannot send a probe there, and our equations break down under these conditions. That uncertainty, that is not a failure of science. That is science doing exactly what it is supposed to do, staring into the unknown and saying, we're going to figure this out. Neutron stars don't just sit there being extreme, they do things. When a neutron star first forms, it starts spinning incredibly fast, sometimes hundreds of rotations per second. For the same reason a figure skater spins faster when they pull in their arms. Conservation of angular momentum as they spin, their powerful magnetic fields beam radiation outward like a lighthouse. Every time that beam sweeps past Earth, we detect a pulse of radio waves. We call these pulsars, and they are so precise, so perfectly regular, that early astronomers thought they might be signals from an alien civilization. They are literally the most accurate natural clocks in the universe. But the most spectacular neutron star event when two of them collide. When two neutron stars are in orbit around each other, they slowly bleed energy as gravitational waves, actual ripples in the fabric of space-time. Their orbits decay. They spiral inward over millions of years. And eventually, they merge in an explosion called a kilonova. And in that moment of collision, for a fraction of a second, conditions become so extreme that heavy elements are forged from scratch, not through fusion. The neutron-rich material of the stars falls apart and reassembles into heavier and heavier nuclei. We're talking about gold, platinum, uranium, iodine, the stuff in your table salt. Scientists now believe that the majority of these heavy elements in the entire universe were created in kilonova explosions. Think about that. The gold in your jewelry, the platinum in your catalytic converter, the uranium in nuclear power plants. All of it forged in the collision of two dead stars billions of years ago, scattered across the galaxy, pulled together into our solar system. And eventually ending up here, stars have to die to create elements. But for the heavy ones, they have to die twice. First as a supernova, creating the neutron star. Then as a kilonova, when that neutron star collides with another and forges the heavy elements the universe needed. Two deaths, billions of years of waiting, and then slowly those atoms drift through space, pulled together by gravity into clouds, into new stars, into planets, into us. The iron in your blood, forged in a supernova, the gold in your ring. Born in a kilonova collision, the calcium in your bones, scattered across the galaxy before Earth even existed. You are quite literally assembled from the remains of stars that had to die twice, so that you could be here, and somewhere out there right now, a neutron star is spinning. A pair of them are spiraling toward each other, and in a few million years, when they finally collide, they'll create more of the elements that some future civilization might one day build their world with. The universe is recycling itself, and that might be the most profound thing I've ever said on this channel. If that blew your mind even a little, hit subscribe, because we're just getting started.